Well, good morning, everybody, and welcome to today's webinar from Smart Vision Europe. Where today we're looking at using SPSS statistics for analytics applications associated with human resources or HR analytics. And if any of you haven't joined these sessions before, you just be aware there's a few FAQs. We do record the session, so you'll be able to listen to it again afterwards. And there's a bit of slideware. There's not a lot of slides, but there's a wee bit of slideware. So we'll email out a link to you so you can download those materials after the session's ended. And if it's particularly useful for colleagues who are unable to attend today, then the best thing to do is to ask us if we can rerun it. If you can get enough of them together, just send us an email or something like that. Reach out to us, give us a call, and we'll see if that's possible. And with regard to asking questions, well, all the lines are muted, so we ask you to use the chat panel. And if we run out of time, we'll follow up with you. I'll try and keep an eye on it, but sometimes we're trying to cram a lot of stuff in, and we have to follow up offline. And my name's Jarlath Quinn. I'm analytics consultant at Smart Vision Europe here. Formerly an employee of SPSS and of SAS and of IBM. I'm actually joined online today by my colleague Rachel Clinton, who's also from Smart Vision, and also by Anne-Marie Mulher from IBM. So they'll just be keeping an eye on things, making sure everybody's logged in correctly and giving me a nudge if there are any questions that come up. If you don't know who Smart Vision are, we are a gold accredited partner to IBM, and we specialize in statistics, in machine learning and AI and data science and all that type of stuff. Now, we do work with other applications like Data Robot and open source applications like R and Python and Spark. We're a relatively small organization, but we have very deep experience going back 30 years at least from some of us, working in analytical software and predictive analytics and data science technology. And that just means that we got a lot of experience of applying these types of techniques and these types of approaches and applications across many different sectors, whether it be the public sector or private sector. It would be applications in retail and healthcare and power utilities and water utilities and uh, advertising and media, um, uh, manufacturing, central government, charities, housing associations, and also fintech, finance and insurance. So lots and lots of different applications where we're bringing statistics to bear. And certainly things like HR applications, which may actually fall across these different vertical sectors, would be something that which we've got some experience of. And we would have used historically a range of different technologies, but certainly the kind of workhorse technology that we would have relied on, probably the first thing we'd reach for would have been something like SPSS statistics, of which we have considerable expertise, and we have a lot of. If you haven't logged on to any of our sessions before, you'll find that when you go on to YouTube and onto our website, you'll find that we've actually got lots and lots of videos talking about different analytical techniques and different approaches and different applications that we've built up over the years. Quite a wide portfolio there. So do check that out. Whether you're new to the software, whether you're new to this approach, or whether you are, you're more experienced in that area. So thinking about the applications we've worked with in HR analytics, it would be things like, modeling employee defection. That would be a common one, organizations are interested in that. They just like people are interested in customer churn. They want to work out the probability that somebody's still going to be a customer in 6 months' time. Same thing, except this time we're dealing with employees. Arguably, with employees, you've actually got a bit more information to work with because you've got internal information, demographic information, so you can and remuneration and compensation information and benefits and things like that, and you can come up with a score, a probability value that says this person actually has a high likelihood of resigning. And you might use machine learning models for that. You might use statistical models, and there's things like forecasting. So that would be extrapolation out into the marketplace and saying, okay, this particular area of the market's growing quite a lot. We should be thinking about hiring people in the fourth quarter because the model indicates that there's likely to be a 10% increase in demand in that area. You have things like benchmarking for salaries, so trying to predict what people's salaries should be based upon market conditions, based upon their skill set and their level of experience. And slightly more obscure applications would be things like absenteeism pattern analysis. So basically trying to figure out whether or not there's an issue with individual employees, whether or not they're starting to exhibit a profile where absenteeism for whatever reasons, health reasons, mental health reasons, or whatever, are going to cause an issue in the past. So, trying to detect patterns or trends in that early on, so that you can intervene and take action which mitigates that. Morale trending, trying to take the temperature of employees and morale. So that could involve, things like surveys. It could involve a lot of unstructured data, looking at reports of people and feedback that they've given over time and using AI technology perhaps to try and classify or categorize that. And then something that we're going to look at is a fairly established approach is basically trying to work out whether or not things like remuneration or work hours are fair and equitable within an organization, or whether or not there's some sort of bias going on, even with the best will in the world, that can start to happen because, of course, organizations tend to reflect the societies that they work within. And in this particular webinar, we're going to look at two examples. We're going to look at an example referring to equity and fairness using classical SPSS statistics, very much the base SPSS, what we call the SPSS base, just classic sort of significance testing type approaching and regression analysis. And then we're going to look at predicting people's likelihood to churn, to defect, if you like, based upon answers that they've given to a survey. And we're going to be looking at using decision trees, which is a module of SPSS which is a very, very nice way to approach that type of problem and produces very visual models for us and can be very useful when we're analyzing things like survey data. So we're going to start off looking at statistics to assess equity and fairness. One of the things that inspired this is the fact that there's a very well-known data set that ships with SPSS. When you buy SPSS statistics, you'll find that there's a folder called the samples folder, and it comes with a whole load of SPSS files, which are used in the tutorials and the help section, of course, to try to illustrate, different approaches and to teach people about how to apply different statistical methods. And one of the most commonly used data sets within there is called the employee data set. It used to be called the bank data set. And it actually is based on some real data that go back to the 1970s and 1980s. And it was based on a data set about employees in a Chicago bank. The bank was Harrison Trust Savings Bank. And in the late 1970s, they were subject to an equal opportunities case where a class action, if you like, was brought against them on behalf of the employees there, arguing that there was discrimination based on pay and the bank's pay and promotion policies, particularly against female employees and I think to a certain extent minorities. It's difficult to find out all the details of it. I've been kind of Googling around trying to find the details, but one of the things that made it more famous was the fact that there was a statistical study carried out by a guy called H.V. Roberts, who used things like significance testing and regression in 1979 to try to show that there was in fact systematic bias and for whatever reason that women particularly the female employees in one of the employment categories tended to be paid less on appointment actually and basically on their starting salary compared to male employees. In fact, by the late 1980s, that bank was settling for a record $14 million. You can see here it says Chicago bank accused of job discrimination against women and minority employees has agreed to pay a record 14 million in back wages. 14 million doesn't seem that much these days, but back then it was a lot, and it was actually I think it was the Department of Labour brought the action against them. And it was a 14-year legal struggle. So you can see that was 1989. So it was going back 14 years. That's how long it took for them to settle. They had to back pay. Okay, so on that basis, having established that, let's have a look at the data set where we're going to start off comparing the mean starting salary for men and women. So if I look back this data set, here's this data set we have. I got it open. It's called employee. I've just added the field age here. You can actually calculate the variable age in using birth date. And there's actually a little tool here called Date and Time Wizard, which will allow you to do that. But I've just added in the age there because it helps me illustrate some other techniques. And one of the reasons why this is a really good data set to work with a lot of the times is because it's uh it's got a mix of different field types, like a date field, it's got category fields, it's got string fields, it's got continuous fields, these number fields. It's got lots of relationships between the different variables within it, and everybody understands it. So if you ever want to kind of test something out, it's usually the first one I kind of reach for. So the first thing I'm going to look at is just do a comparison of males and females in terms of their what's called this field here called sal begin, which is their beginning salary. If I just right click on that and say descriptive statistics, um, it'll just give me a summary of that, right, and tell me what the average is. And it says, okay, look, the minimum was $9,000, the maximum was $79,980. This was the late 70s. And the mean was $17,000, the median was $15,000. So that's kind of the summary stats with that particular field. But if I want to illustrate the difference between men and women, I could compare the averages, or I could do some sort of visual relationship between that. And perhaps if I was going to try to look at a visual representation, I might use something like a box plot here. Well, I'll put gender along the bottom here, the x-axis, and I'll pick up beginning salary, put that into the y-axis, the vertical axis. Click OK. And this is a representation of the two distributions, one for male and one for female. So females on the left side here and males on the right side. And what we notice is, well, first of all, we've got to talk about what we're looking at when we're looking at these boxes. The box itself is the middle 50% of the distribution. So this is the 25% mark to the 75% mark. So this is where the bulk of the middle part of the day, 50% of the people are within this zone. This is the bottom 50% for the males. This is the top 50% for the males. And then all of these numbers outside, these refer to case numbers. So case number 29 is an extreme value, as it's indicated by their asterisk here. It's an extreme, it's an outlier. $80,000 that person earned. That's not typical. So rather than having what's called the whisker of the plot extend all the way up to this point just to accommodate this one case, we plot outliers and extremes. Outliers are O and extremes are stars here outside of that. And you can see there's some extremes for the females down here and some outliers as well. So it's just really a way of saying that these guys are kind of exceptions to the rule. And you could make a judgment whether or not you should be including them or not. But this is where the bulk of the data is. And what we see is that the male distribution is just sort of shifted upwards. Of course, there's a bit of overlap between the two. But you can see that if we take out the outliers and extreme, like the top part of the female distribution is kind of still within the 50% of the male distribution. Now, so it does look like men are compared to women, that their entire distribution of pay is just shifted upwards. But of course, at this point, we have to think, hang on here, are we comparing like for like? If we are we actually comparing people in a similar job category? Well, if we do a crosstab here, I'm going to do a little crosstab and just drill down into this in a bit more detail. I can do a little crosstab here where I look at gender, put that into the rows and break it up by employment category and just ask for some row percentages and some clustered bar charts here and click that, okay. And what we find is that when we look at this, I'll just double click on this and zoom it and straighten it out for you, is that actually for females, 94% of them are clerical workers and only 4.6% of them are managerial workers, whereas for males, nearly 30% of them are managers and 10% of them are custodial workers. There are no female custodial workers, custodial being like facilities. So we're not really comparing like for like. And in fact, the court case was brought by the clerical workers. So we should isolate the clerical group on its own, make sure we're just looking at that group. And we do that by going to data, select cases here. And we create a filter. So we do that by saying, okay, employment category is equal to, well, it's equal to clerical. What's the code for clerical? That's the label, clerical, but the code is code one. So we say job cat, which is employment category, the field name is equal to one. And that will then just filter on that basis. And if I reran my crosstab again, you'd only see one job category in it, which is, of course, clerical. And we have 364 cases rather than 474 cases. And then if I rerun my box plot again, we'll be looking at the female and male clerical workers. Okay, so now there's still looking at the male group here. They're still shifted higher than the female group. We can definitely see that the median value, which is this middle 50 percentile here, the median salary for the males is still higher than the median salary for the females. But we've managed to zero in now on on the group that we're interested in, which is the clerical workers. Okay, let's just boil this down and have a little look at the differences in terms of their averages. So if I want to compare the averages, I'm going to go and say, let's look at the means. And we'll look at gender broken down by beginning salary. And I'll click OK at that point. And it just gives me this little table here. This processing summary is just something you get. I don't really need that. It's just telling me if there's any missing data. And this is the little table we want. We can see the average salary, starting salary for female employees was 12,740. And for male employees, it's 15,861. So more than $3,000 higher. The standard deviation, the amount of spread within the two groups, is kind of comparable. They're kind of similar amounts. And there's 207 females in the clerical group and 157 males. So at this stage, we might want to do some sort of statistical test. Now, technically, you'd want to do what's called the t-test here, but you can also do a test that comes with the means procedure here, which is an ANOVA test called an F-test. Does a similar sort of thing. And basically, all that's doing is giving us a significance value here, 0.000. It's saying that, if I were to double click on that and look at it, and I can see it's 28 decimal places back. So it's actually 0.00028 times 54545. So it's a tiny, tiny number. And it's basically telling me the probability of getting a result as extreme as this, assuming that in reality, the two averages are the same, and that this difference that we're observing is in fact just driven by the fact that we've taken a random sample and we've just got unlucky. Just got unlucky, and it seems like the males are much higher than females. It's telling us the probability that could happen. It's saying that it's definitely less than 1 in 1 million that you'd get a difference that big with sample sizes of this size and standard deviations this big between males and females. So it does look, at this point you might be thinking it's a bit of a slam dunk that the men are definitely paid more than the women on average, and that therefore there's bias, there's discrimination going on within the organization. But at this stage, we're thinking about, well, if we take this to court, would we get away with that? Would we be able to argue that? Well, we've got all these other fields in here. So we've got things like, for example, what their previous experience is. And we've got stuff like education. So right away, people are going to say, well, maybe the men are have a higher level of education than the women. And that's why their starting salary is higher. It just simply reflects the fact they've got more years of education. So if I do a means table on that and do it and check, instead of salary, just check education level in years against men and women. Well, it turns out that in fact the men do in this sample have more than 1 year's education on average, higher than the women. The women have 12.2 years of education on average, and the men have 13.75 years of education on average, and that this is statistically significant. We can see that's 11 decimal places back, so it's 0.000. Generally, it only has to be less than 0.05, but most people would regard that as statistically significant. So it's a lot less than 0.05, it's a lot less than 0.01, and less than 0.0001. So we would say, okay, well, there you go. The defense will argue that, the reason why the men are paid more than the women is because they have more years of education than the women. At this stage, we need to think, well, hang on here, is education actually even related to salary? Is it because we've established that men have more years of education than women, and we know that women get paid less than men, but is there a relationship between this field and this field, education and salary? So now we've got two continuous variables. We can't really take an average of that against that because they're both numbers. So what we might do is establish a correlation on whether or not one correlates with the other. And to do that, we just need to introduce the concept of correlation. And this is something we talk about a lot on our webinars. But suffice to say, a correlation is a way for us to measure linear relationships between two number fields, like in this example, the number of years of education and people's beginning salary, and it will allow us to establish whether or not or how strongly related education is to people's beginning salary. And in these examples, in these screenshots here, we're looking at scatter plots, which are, directly related to correlations because scatter plots kind of illustrate the relationship between two continuous fields. Here, each of the dots are not people, but they are in fact cars, automobiles, and it's showing the correlation between, aspects of the automobile like the horsepower and the vehicle weight. And this is, as you can see, this is trying to form a kind of a line here. This is quite a strong linear relationship. And therefore, we get quite a strong correlation here of 0.859. It turns out that correlation values run from +1 to -1, with 0 in the middle. And the closer they are to these extremes, the stronger the linear relationship there is. So when we compare horsepower against vehicle weight to something like miles per gallon, fuel efficiency, if you like, to acceleration, the length of time it takes to accelerate from 0 to 60, it tells us that cars that take a long time to accelerate from 0 to 60 tend to have more miles per gallon, and that cars that can accelerate from 0 to 60, say less than 10 seconds, tend to be less fuel efficient, tend to have bigger engines. But the relationship's not as strong as the relationship between vehicle weight and horsepower. We can see it's a wee bit more random here. It's still a relatively strong correlation, kind of, most people would regard anything above zero point 0.3 as kind of worth noting. This is kind of modest here at zero point 0.4. Here's a negative relationship going the opposite direction. It doesn't mean that it's not a strong relationship. It just means it's a negative one. I mean, here's horsepower against time to accelerate. Of course, if you've got a lot of horsepower, it doesn't take you very much time to accelerate. If you've got very little horsepower, it takes you more time to accelerate. So we get a negative correlation, not as strong as this one, but stronger than this one, and minus zero point 0.7. So we can start to imagine when we get these correlation values what the scatter plots look like when they're associated with them. And just to show you what a random non-relationship would look like, well, here we have mileage against miles per gallon. And the correlation here is very close to 0. Yeah, so this would be probably non-significant. And it's just sort of saying, yeah, there's nothing going on here. And I simply throw the last one in here, just as a kind of reminder to people that correlations can't see curvy relationships. They can only see straight line relationships. So they just straighten everything out. It can't really, the correlation value here can't see this bend between engine size and miles per gallon squared. Sometimes people take the square root of a number or the log of a number in order to straighten out the relationship between two fields. But it's generally good practice to try to visualize the data. So if we return to our data here and return to the question at hand, which is there a relationship between education and beginning salary, given the fact that we know that men tend to have more years of education than women? And is that therefore a way of explaining why men have a higher beginning salary than the women clerical workers? Well, we might first of all do a little plot here. We might do a little scatter plot here. It's not going to look like the scatter plot that we got earlier on, and the examples I've given you for a reason which will become apparent when I point it out to you. If I click OK here. you can see that you're not getting any values. When we look along the x-axis here, we're not getting any values in between these numbers, and that's because these are integer values. People, it's not recorded as 12.1 years of education or 12.5 years of education, and people tend to drop out of education at key points. So at 8 years, at 12 years, at what's that, 15 years and 16 years. But you could put a line through that and say, is there a relationship there? And it does look like there's a relationship going between those values. But what we want to do, of course, is we want to establish what the correlation is. So if we go here and say correlate bivariate, and I do a webinar on correlations, and we got lots of little videos about correlations, so you can look up that if you want to know more information about that. I can look at beginning salary against education level and ask it to give me the correlation value. It comes out as 0.514. So just to illustrate that, it's better than this. It's weaker than that, but it's still a notable correlation of 0.5. That would actually equate to about over 25% of the variation. So it means over 25% of the variation in current salary can be explained if you factor in education level. So how do I know that? Well, because I know that if I square that number, zero point 0.5, I get 0.25, and it comes out, and 0.25 relates to 25%. This is a statistically significant result. The statistical significance here does not mean it's a strong correlation. It just means it's probably not zero. So, well, we can see it's probably not zero. I mean, it's 0.5. It's not, if it was zero, it'd be like, if it was probably zero, it'd probably down to like 0.1 or something like that. It'd be a very weak correlation. So we know education level helps explain current salary. So that's looking like a good way to explain these differences, given that men tend to have higher education level than women. If I wanted to do a correlation of gender against salary and establish how strong that is, you notice that the variable gender here doesn't show up. It's not there. It's actually not. It's disappeared. And that's because gender here is a string field. It isn't coded as one and two. It's coded as M and F. So I'd need to create a number version of that. So I'm going to do that. You can do that very quickly by using something called automatic recode. And then go with gender here, and I'll just create a variable called gender2. It'll create a numeric version of it. Normally, one wouldn't be able to use a category field. Why is that not work there? Oh, it's because it hasn't. It's ignored it hasn't created a value for this one because, of course, he's been selected out. He's not part of the clerical group. He's actually a manager, so it hasn't created a value for that. That's fine. So wherever there's clericals, it's coded them as we can see, as 2 for male and 1 for female. Okay. Now, because there are only 2 values here, and there's not like 3 or 4 values, which with JobCat, there's 3 values. It means that you can do correlations, because correlations will work with number fields, rating scales, and binary fields, which are 2 values, because it's like a positive and a negative. So I would be able to look at gender against beginning salary here and see how strongly that is. Look, that's also 0.5. Oh, this is interesting now, isn't it? So education level affects your starting salary, and gender affects your starting salary as well. So which one's actually causing the starting salary? Are they independent of one another? Is the reason why gender affects your starting salary really because women have fewer years of education than men, and therefore gender becomes a sort of proxy of education? Because that's what the bank's defense lawyers are going to argue. Now, to establish this, we need to do a slightly deeper analysis. We need to get into something called linear regression. And linear regression here is shown as, if I just illustrate that, is actually related directly to correlations. So we've introduced correlations here. And you've seen that as I've already mentioned, you can take a correlation value, and if you square it, it gives you a value called an R square, because the correlation is called the R value, Pearson's R value. And the R square is effectively a percentage. It tells you how much the percentage overlap between the two fields, like a Venn diagram. It's saying here that the percentage overlap between horsepower and vehicle weight. they overlap by 73%. That's how much variation they share. But if we wanted to express this as a predictive model, if we want to take a correlation and turn it into a predictive model, which is what we're going to do to try to predict people's salaries using gender and using education level, then we need to think about how that works. And probably the easiest way to explain it is to think of how long it takes to cook a chicken. So it turns out, depending on whether you're using a recipe from Julia Childs or you're using a recipe from Delia Smith, that there is a little formula you can use. Julia Childs says it's based on the weight and it should be 77 minutes per pound plus 45 minutes. Delia says it should be 20 minutes per pound plus 20 minutes in the end. But it doesn't matter because both of them relate to a formula. And the formula that's shown is the formula for the straight line. And depending on whether or not you're a statistician or a mathematician, you might express that formula as y equals mx plus c or y equals a plus bx. But in either case, you're going to have this 7 minutes per or 20 minutes per. That's called the coefficient, and that's the m or the b value here. The weight is the x. And then you're just going to add on a number at the end, which might be plus 45, or in this case, a plus 20. And that's called the constant in the equation. So if I wanted to build a regression model, I'm going to do that, and I'm going to show you how you can predict somebody's current salary, starting salary based on their level of education. And I'm going to go to regression here and go to and ask for basically a standard linear regression with a dependent variable. The thing I'm trying to explain is their beginning salary, which is what the point of the court case is. And I'm going to use their education level to begin with. So I'm going to click that and click OK. Now, what happens is when you do that, it gives you a bunch of different output, but they're not too difficult to understand. Notice that at the start here, it shows you the R summary, the model summary. Sorry, it says R here 0.514. That is exactly the same as that correlation value, which is R 0.514. And I said if you square that, that's going to get you more than 25%. Well, actually, if you square that, it gets you 0.265, which is called the R square value. We usually use the adjusted R square, which is 0.26. That means 26 of the variation, 26% of the variation in starting salary can be explained using education level. It gives you a significance test that tells you whether or not this model that you're building is actually better than just taking the average, just better than a random wild guess, if you like. And if it's significant, then it's saying, yeah, it's better than a wild guess. And we pretty much always expect it to be significant if any of these variables that we're using are reasonable predictors of the thing we're trying to predict. And then it gives me my little formula, which is, my y equals mx plus c. This formula here, it's actually giving me these numbers here, the constant and the coefficient. And here they are. Here's the constant. It says the minimum is 5,817. And then it gives me a number called 642. Well, that's $642. That's $5,817. That says for every year of education you get $642, and then you add on $5,817 at the end, and that gives you your prediction. And that helps you predict what people's current salary is. And it will be accurate to within like 26%. So not massively accurate, but reasonably accurate. So that means if you have 10 years of education, you're going to get $6,000, $6,400 plus $5,817. So you're getting about $12,000. And with 20 years of education, that's of course going to be then, it's going to be like $12,000 plus $5,818 on the end. And that's just how the formula works. So it turns out I can use this to predict people's current salary. And I can also, as we can see, if I swap this out, I can also use my new gender variable to predict it. And look, if I put that in, it says, oh, well, that gets you an R square, just R square 0.28, 28%. And we can see that here the formula is different. It's saying if you're if you should be adding on 9,619, and because women are coded as 1, If you're a woman, you should add on 3,121 for if you're a woman. And if you're a man, it should be two times 3,000 because men are coded as two. It should be two times 3,121. So men get about £3,000 more, $3,000 more. So for a male employee, on average, we'd expect it to be what 6,242 plus 9,619. So, you're getting down to like, $15,000, $16,000 or so, and that's what the man's salary should be. So now we've got this problem because we know that one thing predicts the salary and the other thing predicts the salary as well. And we're saying, well, which one's important? Well, this is the bit we're leading up to. If I go back and I run my linear regression now and I put education level in here and gender at the same time, then what will happen is if gender isn't if gender is actually not a predictor of salary, and what's really happening is that education level is a predictor of salary, then what we'll find is that gender will not be statistically significant in the model. It'll have a very weak coefficient, and it won't be contributing anything to it. And if it turned out that education level isn't actually what really predicts it, it's actually gender, and it happens to be that men tend to have more years of education than women, then we would find that education level doesn't become significant. This is called controlling for, and this is what we want to do. We want to, the prosecution says, okay, we need to test this out. We need to say, even when we factor in education level, when we control for that, is there a difference between men and women in terms of their beginning salary in this bank? And when we click OK at that point, what we find is we're now using two variables to predict it. The R value goes up to 0.6 and the adjusted R square goes to 0.4. So 40% of the variation in beginning salary can be accounted for using gender and people's years of education. This, of course, is statistically significant. It's better than a wild guess. And when we look at the coefficients here, we end up with a more complicated formula where it says, okay, what you need to do is if they're a woman, you need to add on 2,383, and then you multiply their years of education by $474, and then at the end you add on a constant of 4,565, and that's your prediction for their starting salary. And if there are men, you add on two times 2,383. You add for every year of education $474, and then you add on your constant at the end, and that will be the prediction for the men. We're just adding an extra term. But the critical point here is that the constant's significant. It makes a difference. It's still important to have it in there. But gender is also statistically significant, and education level is also statistically significant. So what we're saying is when we control for education level, when we control for it, let's assume they all have the same education level, then gender is still a significant contributor to predicting whether or not it's still a factor that predicts what people's level of starting salary should be. It's quite a significant factor too. In fact, we can see that it's $2,383. So they can't really argue on this basis that what's driving the difference between men and women in terms of the salary is that in fact that you have this hidden factor, which is education level, and the way in which we can start to statistically prove that is by using things like linear regression to do that, and doing what's effectively called a multiple linear regression. You could go back here and you could actually add in, other factors. You could actually add in things like previous experience in months. Because okay, maybe the men got more previous experience in months, and we could put that in. Previous experience in months is also statistically significant. It's very weak. It actually you only get $3.50 for every previous experience in month, and it's statistically significant. But it doesn't negate gender again. So even as we add in other explanatory variables here, even if they're quite weak, it doesn't help us explain this difference. And this is why using significance tests and using things like correlations and using things like linear regression can help us identify what's really driving differences in a key outcome, such as people's beginning salaries. And certainly, the judge found that some of the statistical evidence that was presented was pretty compelling. Okay, so that's our example of using HR analytics, where we're basically using it to do an audit, if you like, to help us ensure equity and fairness. What about if we wanted to use a completely different approach here, where we're trying to use decision trees to model employee retention? So this is a completely different data set and a completely different approach at this stage. So um, let's just have a quick look at that. So first of all, we need to introduce the concept of decision trees. Decision trees are used to build profiles. So they're used for three things. They build profiles. They literally show you a visual profile of things like customer behavior, staff behavior, patients, students, machinery, anything, whatever the thing is that you're studying. In doing so, it helps you find key segments, key groups that elicit, very different behavior from other groups. And it also effectively generates a predictive model. And decision trees are really popular because they're quite visual representations of models, in the same way that, linear regression we saw there isn't a visual representation. It's just a set of numbers that relate to an equation. And they're relatively easy to understand. And the way in which I normally introduce it is by using a very famous data set, which is the Titanic data set, where we say what are the most important factors determining survival during the sinking of the RMS Titanic. Given that 32% of people did not survive, sorry, 68% of people did not survive and 32% did survive, you might ask, is it gender, or was it their age, or was it the class that they were traveling in? A decision tree helps us figure out the hierarchy of factors, because it turns out that if you were to do a series of statistical tests where you test gender against survival and age against survival and class against survival, what you find is that they're all statistically significant. In fact, you find that gender, that 73% of women's passengers survived. There was only 470 women on the boat compared to 1,700 men, something which isn't always reflected in the movies. Only 21% of the males survived, and that this is statistically significant. This is based on what's called a chi-square test. It's a different type of test. And again, if you're not familiar with that, you might want to check out our webinar. We've got some recordings of webinars on interpreting statistics tests or interpreting tests of significance. We see a similar thing when we look at age, adult and child. 31% of adults survived compared to 52% of children. It's not as big a difference. 73 to 21% survival, 31 to 52, not as big, but still statistically significant. And when we look at class of travel, we can see that 62% of men survived. Sorry, of first class travelers survived. 41% of second class travelers survived, people traveling in second class. Of third class passengers, 25% survived. And of crew, 24% survived. So it does look like this is sort of step change. The further down the pecking order you go, the lower your chance of survival. So when we build a decision tree, what a decision tree does is it finds the variable which has effectively the smallest p-value, because the p-value here we can only see the first three decimal places. If we could stretch it all out to show all the different decimal places, sometimes it might be like 64 decimal places. It finds the value which is the most significant, if you like, and it starts to build the decision tree. So the top of the decision tree related to survival here looks like this, where we have, the key variable, the variable which is the most important one. In this case, it happens to be sex. It happens to be their gender. And you can see it immediately ticks the 2,201 passengers, where there's an overall survival. This is our baseline. This is called our dependent target field, the survivability. 32% survive. It splits it into males and females, and we get 1,700 males over on this side of the tree and 344 males, females over on this side of the tree. And it then shows us, it highlights whichever is the larger group, just puts a little gray symbol around it. So here it says 78% of men survive, 73% of females survive. It says this is the most important factor because it's got the smallest p-value using a chi-square test again. And in fact, if we expand the whole thing out and get it to build the whole tree, it's only got three variables in here, and they're very simple variables. We can see that there's a pattern that says, okay, look, of the 1,731 males, the next most important factor is whether or not they're an adult or a child. and it splits off the adults, which are 1,667. It says if you're an adult male, only 20% survived, whereas if you're a child male, 45.3% survived. And if you're an adult male traveling in first class, 32% survived, second class, 8% survived, third class, 16% survived, and crew, 22% survived. So it turns out the people who were the least likely to survive are, in fact, adult males traveling in second class at 8.3% survived. Over in the female branch, remember, we've only got 474 cases here, only 474 passengers traveling. It doesn't use the variable age. Why not? Well, because either there weren't any female children traveling, which I probably not true, or it simply wasn't statistically significant. It didn't make a difference to the survival, so it doesn't use it. And secondly, when it uses the variable class at this point, it actually starts to group together. Notice second class and crew are grouped together in the female branch here, and that's because they're not statistically different in the female branch in terms of their survival chances. So it's just grouped them together. So that's really useful because it's creating a kind of a simple, a simpler tree for us to make sense of. 97% of females traveling in first class survived. 87% in second class or crew survived, and 45%, 45.46% in third class survived. That means everybody ends up in one of these, these are called terminal nodes. It means you end up in one of these final boxes down here. If we count them across, it's 1, 2, 3, 4, 5, 6, 7, 8. That means there's 8 probability values, and the probability values are simply just your chance of survival, whether it be 8% or 97%. And it's going to generate for the entire data set 201 passengers. It would generate 8 different probability values telling you your likelihood of survival. This particular type of tree is driven by chi-square, and it's called the chi-square automatic interaction detector, or a CHAID tree. There are other types of decision trees that the SPSS module runs as well. And notice also that every one of these little groups it creates is called a node, and it gives it a number starting with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are in many ways like segments, little groupings, so they're finding hotspots within the data. Okay, having established how a decision tree works, let's jump out to a different data set now, and I'm going to open up a different data set. Let me just make sure I switch off everything here so I don't confuse it. So I'm going to select cases, all cases, click OK, and then we'll open up a different data set. I'm actually going to get rid of this output here because we don't need it anymore. I'm opening this data set called hrsurvey.sav. This is actually a survey data set. This would work perfectly well with operational data, with HR data, but in this case it's effectively anonymized. And we can see that we have information here such as what sector people in this survey are working in, what their job type is. So we can look at look at all the different job types. There's 1,000 cases in here. There's 24 cases where we don't know what their job type is, but you can see it's everything from senior management down to like driver. A lot of different groups there. We've got years employed, and then we've got a whole bunch of fields here, which are rating scales. And we look at the names of the rating scales here, you can see it's things like, what's your level of satisfaction, or how positive are you with them, uh, admin and organization, attitude of senior staff, attitude of finance staff, attitude of tech staff, relationship with other workers, training and induction, performance and feedback, crash facilities, challenging job. We've got a variable here like gender. And then we've got this critical variable at the end, excuse me, which is basically ask them, how long do you intend to remain with the organization? So presumably this is sufficiently anonymous for people to say, to give an answer. Are they giving an honest answer? We don't know. But some people say they will, as we can see, some people say, I'll leave within 2 years, 25%. Or I'd like to leave 2 to 5 years, probably, 25%. And about half of them say, I'll remain at least 5 years. So there's 3 groups here, not 2 groups in this case. And if I want to build a decision tree here, I can go down to classify and down to tree. And I tell it what my key field is. My key field here is when an employee leaves. This key field could also just be overall satisfaction with your job, something like that to help you build a profile. And what I'm going to do is I'm actually just going to start off here and I'm just going to pick up the demographic stuff, which is, not the rating scales here, and just chuck that in. So I can start off slow and careful and just say, okay, I'm building a shade tree here. And just say, are there any of these factors? Are they statistically significant? Are they related to when employees leave? And I click OK at that point. It produces a decision tree. It only chooses one of these factors. So up to 1,000 cases, I can open this tree and I can zoom into it. There it is. And it's choosing the variable age group. So all the other factors were not significant. And you can see that it highlights the biggest group here. You can also see that I can actually just show it as tables, where gold is remain at least 5 years and the cool blue is leave within 2 years, or I can show it as a table or as a chart or as a table and as a chart together. And as we can see that the younger people here, which are group 25 to 34, group B or less, that's the younger age group, so people under 25, they're the people who say that they are most likely to leave within 2 years, 34%. The next group says B to C. Well, B's already in that group. That's a bit confusing, so I'll just change how it's labeled. I'll change it to label ranges as text. It says higher than B through C. That just means through C, well, that's 35 to 44. It just means the C group here. So people aged 35 to 44 are in node 2 here, and 19% of them say they'll leave in 2 years. And then we get higher than 34. This is that'll be group D. People higher than 44, group D, 35 to 44. Only 9% of them say that they will leave within 2 years, and 67% say they will remain at least 5 years. So we know that age makes a difference, that younger people are more likely to intend to leave than the older people. That kind of makes sense that they would settle down into their job over time. What happens if I go back to this relationship here and I say, okay, let's chuck in all of the other factors, all of these rating scales where they've been asked about these different aspects of the work. Click OK. Run that again. And it creates a slightly more complex tree for us. Creates a different more tree for us. And we'll just zoom into that and have a look at that. Um, so I just zoom into that, and again, I'm going to ask it to show the colors. Remember, it's like blue means leave in 2 years, and gold means stay at least 5 years. So it's almost like a filtration system. Let's just change this to 125% so we can zoom out. And you can see here that the single biggest factor now is different. It's saying that, again, if I change this to ranges as text, it's saying that attitude of senior staff is the single biggest factor. And it says if people say fair, if they give it a score of 3 or less than 3, then 82% of them say I'm going to leave within 2 years. And if they say the general environment is 3 or less, scores 3 or 5, then that jumps to 93%. Okay. If they say the attitude of the senior staff is better than fair through to good, that means if they just say it's good, category 4, then 33% say they'll leave within, or 34% say leave within 2 years. But if they say the working hours are scoring 3 or less out of 5, then 53% say. But if they say it's better, working hours are better than 3, then only 13% say they leave within 2 years. And then we get into factors like general admin and organization and holiday entitlement. And of course, over the far end here, we have people at the other extreme saying they say that attitude of senior staff, senior management is better than good, better than 4, category 5. Then 75% say they'll remain for these 5 years, and if they think their working hours are better than good, then 96% of them say that they'll remain at least 5 years. Now, at some point, these trees stop. You can see they get down into group sizes here. The group sizes here are 90, 69, 106. They may stop at a certain point, and they stop because either they can't find any more statistically significant factors to add in, or because the group sizes get too small. So you can actually ask it to give it permission to build a more complicated tree by going to criteria here and say, look, I'll allow you to create a group size as small as 20, just 20 cases in there. And the parent node before that can be 40 before it splits. And that might create a slightly more complex tree for you. So you can do that. It might create probably not in this case, but yeah, you can play around with the factors here and try other different types of decision tree. But yeah, so you can see here that now when I do that, it added to the senior staff for people scoring 3 or less. It's working hours again, which is really driving it, and then things like training and induction. So it gives the employers and managers attitude. It gives them information about what are the things that need to get right if they wanted to maintain their best employees. And in fact, I can ask it at this stage to predict. I could apply it to a new data set and ask it to predict, or I could just ask it to save the predicted value and the predicted probability and click OK. And it would rerun that and it would create these extra fields at the end here. I just make this a bit wide. This is wider. This is predicted value. That's a predicted value of, that's a predicted probability of being category one, category two, category three. And if you can't remember what the scores and what these values mean, I can actually just copy and paste them from one to the next. Just copy the labels over. There you have. So it says, okay, well, I predict that this person will leave within 2 years. What's the probability of that? 68%. I predict this person will remain at least 5 years. What's the probability of that? It's 100% because everybody in that group that this person belonged to remained at least 5 years or said they would remain at least 5 years. So it's giving me the probability of them leaving within 2 years and the probability of them staying at least 5 years. And that again can be very, very useful. Okay, that takes us to the end. That helps us look at 2 examples of where we could apply SPSS statistics to 2 very different types of HR applications. One where we're trying to audit fairness, equity, using significance tests, things like correlations and regression. And a second example where we're using decision trees to build profiles or to model people, maybe best based on survey data, maybe based on data that we have about their performance, operational data, their salary, their demographic information. We could do exactly the same thing. So decision trees can be used in multiple ways, and I'd encourage you to have a look at them. Something else to bear in mind is that in all of these examples of decision trees, I was using category fields. One of the things I find really useful is if you use a continuous field in there, if you've got something like salary, it actually finds the thresholds, the points in the fields where it makes a difference. So you could say, what somebody's pay rise was, something like that, and see how the most recent pay rises, and see how that affects their likelihood to do something or their level of satisfaction or something like that, and it will find the actual thresholds for you within those groups. So really powerful in that sense. In the meantime, just a quick note on working with Smart Vision Europe. You should be aware that we can help with processing and analyzing your data, and we offer a lot of training, self-paced, virtual, and in-person training courses on how to use SPSS products and appropriate statistical techniques. We also offer a mix of consultancy and training whereby we do the initial work and then teach you how to replicate it. With regard to sourcing your software, you can buy your analytical software directly from us, often with discounts. And we can assist with the selection, piloting, and implementation and support of analytical tools. And we even have our own web store where you can buy SPSS online. As I say, training, a formal classroom, virtual training, or bite-size or online self-paced training. We actually have our own library of training courses that is free to our customers. We offer no strings attached technical business advice relating to all things analytics, and technical support services around the IBM SPSS product line. In the meantime, we hope you found that useful. Do stay tuned and check out our website. You'll see that we have a portfolio of other webinars that we have run in the past. We've recorded. We also have webinars that we're running in the future, and you'll see those ones coming up. You may find that some of them are actually useful and interesting to you as well. So I do hope you find that useful and that you log in again in the near future. Thanks very much.